How do you get fast internet on a ship in the middle of the ocean? It's beamed down from space. Here's how satellite internet like Starlink actually works and why the new version is so much better than the old one. The old way used one big satellite, parked 36,000 kilometers above the equator. At that height, it orbits exactly as fast as Earth spins, so it hangs over the same spot forever. That's called geostationary. But 36,000 kilometers is far. Your data has to travel up there and back down twice for every request. Even at the speed of light, that round trip adds about half a second of lag, often more. Half a second is fine for beaming TV, but for video calls and gaming, it's painful. Every click feels delayed. The new approach flips the design. Instead of one satellite far away, you launch thousands of small satellites in a low orbit, around 550 kilometers up. That's about 65 times closer. 65 times closer means the lag almost disappears. Latency drops to a few dozen milliseconds, good enough for video calls, gaming, and everything else you do online. But there's a trade. A satellite that low can't hover over one spot. It races across your sky in just a few minutes. So you need a huge constellation, and your connection constantly hands off from one passing satellite to the next without you ever noticing. That's why the dish looks flat. It's a phased array, hundreds of tiny antennas that steer the beam electronically, tracking satellites across the sky with no moving parts. Up in orbit, the satellites also talk to each other with laser links, passing your data across space. Eventually, it drops down to a ground station, a big antenna farm wired straight into the internet. And the answer comes back the same way. One honest note. Mega constellations mean thousands of new objects in orbit, something astronomers and space traffic trackers are watching closely. So why does this matter to you? 1. It's real broadband anywhere cables don't reach. Rural areas, ships, planes, disaster zones. 2. It's why the dish needs a clear view of the sky. It's constantly tracking fast-moving satellites from horizon to horizon, and trees or walls break the link. 3. Latency now rivals ground internet for everyday use. Space internet has stopped being a last resort. So that's the trick. Don't park one satellite far away. Fly thousands of them close, and never stop handing off. I'll see you in the next one. A 20-story metal tube falls back from space, lights its engine at the last second, and lands standing up. No pilot. Here's how a rocket lands itself, and why the hardest part is that it physically can't hover. A returning booster is like a falling pencil you're trying to balance. Tall, mostly empty, and screaming through the atmosphere. On the way down, it steers with grid fins, waffle-like paddles near the top that fold out and bite the air to tilt the whole rocket. Then the engines relight. First a re-entry burn to slow it down before it slams into the thickest air. And then, seconds before touchdown, the landing burn. Now the wild part. This rocket cannot hover. Even one engine at minimum throttle pushes harder than the near-empty booster weighs. The instant its speed hits zero, it starts climbing again. So it performs what engineers call a hover slam, also known, honestly, as the suicide burn. The whole trick is timing. Start the final burn so the rocket speed reaches exactly zero at exactly ground level. 0 meters per second at 0 meters altitude. Burn too early and it stops in midair, climbs, and falls back down. Burn too late, crater. So how does it nail it? GPS and inertial sensors feed fast onboard computers that resolve the entire trajectory many times a second, all the way down. Touchdown happens on a landing pad back near the launch site, or on a drone ship floating hundreds of kilometers downrange. So why does this matter to you? The booster is the most expensive part of the rocket. Flying it again, instead of throwing it away, slashed launch costs roughly 10 times. Cheaper launches mean more satellites. The satellite internet we covered last time, weather forecasts, science missions, the space economy you already benefit from. And remember what it really is. Not magic, just precision timing. The same math problem resolved over and over, faster than gravity can win. So, fall, steer with fins, burn twice, and hit zero speed at exactly zero altitude. That's how a rocket lands itself. I'll see you in the next one. A satellite has no engine holding it up. Nothing is attached to it. So why doesn't it just fall out of the sky? Plot twist, it does fall. It's falling right now, constantly. Let me show you. 300 years ago, Isaac Newton imagined a cannon on top of an impossibly tall mountain. Fire it gently, and the cannonball curves down and hits the ground nearby. Fire it faster, and it lands further away because the Earth's surface curves away beneath it as it falls. Now fire it fast enough, about 28,000 kilometers per hour, and it falls all the way around the planet and never lands. Falling forever and always missing the ground. That is an orbit. And those weightless astronauts? They're not beyond gravity. Up there, gravity is nearly as strong as on the ground. They float because they're in continuous free fall together with their spacecraft. Now, different heights mean different jobs. Close to Earth, you orbit fast. The ISS laps the entire planet in about 90 minutes, and satellite internet constellations live down there too. Go higher, and every lap gets slower. And at exactly 35,786 kilometers, one lap takes exactly 24 hours. The satellite turns with the Earth and hangs over one single spot. That's geostationary, perfect for TV and weather satellites. One more thing. The lowest satellites brush the wispy top of the atmosphere, and that tiny drag slowly pulls them down. So they need an occasional boost. The ISS does this regularly, where they re-enter and burn up, which is also how low orbit cleans up after itself. So why does this matter to you? 1. This is the physics behind your GPS, your weather forecast, satellite internet, and satellite TV. Each job is parked at exactly the right height. 2. Weightless just means falling. Astronauts aren't floating beyond gravity. They're falling around the Earth. A perfect myth-buster for your next dinner conversation. 3. Low orbit is self-cleaning. Dead satellites get dragged down and burn up, and that's by design. So that's the secret. A satellite is simply falling sideways so fast that it keeps missing the ground forever. Now you know. I'll see you in the next one. Right above your head, a few hundred kilometers up, there's a traffic jam. Decades of rocket launches have left Earth's orbit littered with junk, and today we're looking at what's actually up there and what we're doing about it. First, the junk itself. Dead satellites that simply stopped working, spent rocket stages left behind after launches, and fragments from old explosions and collisions. Radar networks currently track tens of thousands of objects. And beyond those, there are millions of pieces too small to track at all. Now the physics problem. Everything in orbit moves at roughly 28,000 kilometers per hour, and two objects can close on each other at tens of thousands of kilometers per hour. At those speeds, even a fleck of paint hits with the energy of a bullet. Which brings us to the famous worry called Kessler's syndrome. One collision between two large objects can create thousands of new fragments. Each of those fragments can then hit something else, creating even more fragments. A runaway cascade like that could make busy orbits hazardous for generations. But here's the part the headlines skip. The risk is real, but it's gradual. A slow creep over years and decades, not a movie explosion. And the better news? A lot is already being done about it. 1. Radar networks track the junk, and satellites dodge it. The International Space Station performs several avoidance maneuvers every year. 2. Modern rules require post-mission disposal. When a satellite retires, it either deorbits to burn up or parks in a graveyard orbit out of everyone's way. 3. Low orbits actually clean themselves. A thin wisp of atmosphere drags debris down over the years until it burns up. And 4. The first cleanup missions with robotic arms and drag sails are already flying demonstrations right now. So why does this matter to you? Your GPS, your weather forecast, your internet, and your TV all live up there. Space junk is a threat to services you use every single day. The new mega constellations, thousands of satellites strong, are now designed to deorbit themselves when their job is done. And space sustainability is quietly turning into something like air traffic control, boring, vital, and very solvable. So next time you look up, remember, it's crowded up there, but it's tracked, dodged, and increasingly cleaned up. That's space junk. I'll see you in the next one.